Good afternoon. The topic of my project is an inverted pendulum. The reason I picked this project is because it's a good example of a system that is unstable and it requires some sort of control to be able to stabilize the system. An inverted pendulum, unlike a traditional pendulum, has the center mass above the pivot point and is typically attached to a moving cart. See that thing going on? Let's try a different color. Here, this box represents the cart with some external force acting on the cart, and the pendulum is usually attached to the top of the cart. While the cart experiences a linear displacement, the pendulum is experiencing an angular displacement. Modeling the motion of this system can be quite complicated because first you've got to model the motion of the cart in addition to model the motion of the actual pendulum. This is a very common system, and a good example of this would be a rocket that's taken off. If the rocket is grounded, one might ask, well, the rocket is grounded, there's nothing below it that's moving. But we also have to remember that the Earth itself is moving, so this rocket naturally wants to tip over. So we've got to be able to have some sort of control system that can account for the motion of the Earth while keeping this rocket balanced before takeoff. In this project, what we're going to do is we're going to take this system and we're going to establish a mathematical model of the system, and by this we can establish the equation of motion, and this will be for both the cart and the pendulum. Why is this important? Well, if we establish an equation of motion, it allows us to understand how this external force and the magnitude of this external force would affect the angular displacement that our pendulum is going to experience. How do we do this? Well, we do this by first isolating both of these as two separate systems. So I would first isolate the cart and establish an equation of motion for just the cart. After which, I can now also isolate the pendulum. And also establish an equation of motion for the pendulum. The question now becomes, how do we determine our transfer function? Because the purpose of this is to establish the transfer function that gives us an understanding of how our input affects our output. Well, we know that our input is going to be the external force associated with the cart, and our output could be described as the displacement of the pendulum. Before we can get to that, we need to first establish a free body diagram of both the cart and the pendulum. It's safe to say in physics, we know that this force has to be opposed by some friction factor. And we also have to account for the mass of the cart itself, and that is also acting down. And we also know that to the opposing the mass is also our normal force, which is equivalent to the mass of the cart itself. And we also know that the friction can also be a function of the normal force. Once we establish these few parameters, we can then equate some of these to the system modeling equations that we've been working with in the past, where your friction factor can be equivalent to your damper and so forth on. So once we establish the equation that governs the motion of the cart, we can now focus on the equation that governs the angular displacement and motion of the pendulum. In the same way, we would also have a mass associated with the pendulum. This mass is going to cause a gravitational, it's going to cause the weight of the pendulum to act along the center towards a straight line. And we also know that this pendulum is being acted on by some external force, and we'll call it, in this case, P. This external force is derived from the motion of the cart. So this external force is what's driving the pendulum. And it's also good to note that we're also going to have some normal force and some resistance to that motion. So in a nutshell, once we establish the motion of the cart, we establish the motion of the pendulum, we can now write a transfer function as letting F be our input and angular displacement be our output. So we'll call this theta F over F of S. This is going to take a lot more work. You're going to have to first establish the equations, take the Laplace transformation of these equations to get in the S domain, and do the same thing for the angular displacement, and then equate them to each other, do some algebraic work to get it down to where we can see the transfer function. Now, once we establish the transfer function, we can move on to build the block diagram. And all we want to see is a block diagram that is going to have a transfer function we're going to have our input and our output. Now, this is an open system. This is not a closed system, so we're not going to have any feedback in past case where we know that we got to constantly adjust our input to achieve our desired output. The controller itself, the transfer, but the controller aspect of the system will automatically do that. Another thing that's worth mentioning in this particular project is to better understand the relationship that this force has with this displacement. We have to convert this motion into a linear motion. And this also allows us to derive our differential equation. Then we can begin to take the Laplace transformation of that equation to get our transfer function. And from that, we can now use the state variables to take our transfer function and put it in state variable function, which will produce the matrices that's necessary for MATLAB and other application softwares to be able to run simulations and give us some insight on how this force is affecting the pendulum. Thank you very much.